Welcome to this lecture on model specification. I'm excited to start this lecture because we are now getting into structural equation modeling. Over the past couple weeks, we have covered an introduction to structural equation modeling and reviewed the basics of correlation and regression and a few other pieces. Today, we get into structural equation modeling. In this lecture today, we're going to cover specification, which covers the first piece of two, the next being identification, on how to create and draw out structural equation models. So the first piece I kind of want to remind you of is just the basic steps in actually conducting structural equation modeling. So the first step of this is specifying the model specification. That is the focus of today's or this current module. The next piece is to evaluate model identification. That will be the focus of the next module, next week's module. Identification is all about evaluating degrees of freedom, whether you are over, under, or just identified, whether your model is over or under or just identified. We need to have a model that has either 0 or a positive number of degrees of freedom. When you have negative degrees of freedom, your model cannot work. The third step is selecting measures. So once you have identified your model, it is then to select measures, and that can be collecting or examining if you're doing secondary analysis, cleaning, preparing the data. The fourth step is then to estimate the model. So today we're covering model specification. The next module will cover identification, and then in 2 weeks, 2 modules from now, we will cover estimation. So that'll be when we cover about how to evaluate model fit, interpret model parameter estimates, data requirements, different pieces like that. After you estimate the model, then an important piece of this is respecifying the model if necessary, which it very often is, and to also consider alternative models. And then after we're done with that, it's to report the results. So Klein, in your textbook, has a wonderful decision tree, which I have re-put right here with a few little changes in here to, I think, make it a little bit more clean for you and how you go through this. So you'll first start with model specification, and when you're doing that, you'll then look at the model identification. If it meets the requirements for model identification, you move on to selecting your measures. If it doesn't, then you need to re-specify the model. After you've selected your measures, then you estimate the model. You run it and see if you have adequate model fit. We'll cover that in 2 weeks, in 2 modules from now. If it does have adequate model fit, you go on to interpreting the results. If it does not have adequate model fit, then you examine to whether you should re-specify the model in order to figure out why it didn't fit. Most of the time, you'll re-specify the model. You'll identify what perhaps isn't wrong or what maybe needs to be added to make it work. But there are times where you shouldn't re-specify the model. That actually is very interesting and important to report this model as not fitting, that it doesn't fit the way we think it is. This is often very important in theory development, when we develop this theory and then we test it and we see it doesn't fit. However, even when we do that, what we'll typically do is keep the model as is and show, see, it doesn't fit, and then we'll re-specify it still to show how this theory needs to be changed or adapted, or our hypotheses need to be changed or adapted to be able to work. So even if we say no and we still report it, we still usually go back and change it anyways, and we report both in our articles. After you interpret the results, you consider alternative models, alternative ways that perhaps the relationships could exist. And then once you do that, you publish the results. And if you do, going back to the alternative models piece, if you do decide to, if there's an alternative model, you go back to that specifying, identifying, usually you're skipping the select measures because you're using the same measures and you're testing model fit and interpreting the results. All right, so starting with the first piece, that first step, model specification. I'm going to do a quick introduction to model specification and identification before we get into more depth. So model specification is the representation of your hypotheses in the form of a structural equation modeling. So specification is all about what you draw out in your model. What measures are there? What arrows are there? What relationships are you proposing? So much more simply, it's just the process of developing a set of interrelated hypotheses, because your hypotheses are going to be related to each other in this model, drawing those out pictorially, and then making sure it follows the rules of SEM. with both specification and identification. So in order to specify a model, you'll then need to answer two questions for yourself. What are the rules around drawing models, and what kind of hypotheses are possible to ask? Once you open up your mind to the possibilities of what kinds of questions we can ask, beyond just the questions of associations between variables, you can open yourself up to potentially asking much more interesting and relevant and important questions. So we're going to first kind of start off with a few of those pieces around the rules. The rules we're going to cover a little bit today and also next week in the next module in identification. The kinds of hypotheses we're going to cover at the end of this. So identification is all about the process of evaluating the model parameters and degrees of freedom. Models must have a unique estimate of every model parameter. There are problems in your model when a parameter has multiple possible estimates. So the way that you determine this is evaluating the degrees of freedom in the model, and that's done by looking at the how many observations you have. And what I mean by observations are not the number of participants, but if you create a covariance or a correlational matrix with all the items that you had in your analysis, how many cells do we have? And there's a simple formula that I will show you today and also go into more detail next week where you can evaluate that. So essentially what you're going to do is evaluate the total number of observations to the total number of parameters and just subtract one from the other. And that's going to give you your degrees of freedom. We need to have at least 0 or greater than 0 degrees of freedom in order for the model to work. If you have negative degrees of freedom, essentially what happens is that you have more than one estimate for every possible parameter. And we need a unique estimate for every model, every parameter in the model. But we'll cover a lot more about identification in the next module. So now let's go into depth into specification. And we're going to talk about the different concepts within here that are important to consider. The first one, the first piece in specification is what to include in your model. This is the first and most common error. And that error is often not including important and key variables in your model. So in other words, you make your model too simplistic or you leave out key constructs that are really important. This is why conducting a proper literature review is so critical. You know, back in that first lecture when we talked about the importance of knowing your area and knowing your literature is so important because failing to include a critical variable that is very much founded in the literature to be related to what you're talking about could be a really big error in your model that you're not assessing for. At the same time, this is a quote from Klein, in more established areas, sometimes there is too much information. That is, so many potential causal variables may be mentioned in the literature that it is virtually impossible to include them all. To cope, the researcher, that's you, must again rely on his or her judgment about the most crucial variables. So if you're in a new research area, this is a little bit easier to make sure you're including what we're seeing is important. If you're in a more established research area, you really need to pay attention to what are the big players, what are the most common variables and the ones that are most related to what you're working on. And including a few of those is absolutely important because leaving out a variable is the first and most common error in model specification. Next is how to construct hypothetical constructs. So we talked a lot about this back in multivariate, but this is all about making sure that your measures have really good psychometric characteristics. We need to make sure that they are reliable and valid measures when you're doing this. And there are essentially two kinds of measures that you can develop or use. You can have a single indicator measure where you just have one item. This is a single question or a single item in SPSS. Whenever you have a single item, you will almost always have reviewers highlight this as a major concern of the methodology. So it's really important that if you have one item, you can really back that item up and make sure that it's really strong. And at the same time, make sure you're addressing that in your limitation section. Now, when you're doing secondary analysis, sometimes you have no choice because they only asked one question about this. Again, make sure if you're going to use it, it's a good one, and make sure that you address that in your limitation section. What's much better is to use multiple indicator measures. So in this, we have largely two kinds of multiple indicator measures. We have composite variables, where you take a set of items and then you either sum or mean them together, or you have a latent construct. We're going to get into latent constructs probably in about 3 weeks, if I remember the syllabus correctly, when we get into confirmatory factor analysis. There are really big benefits to doing a latent structure versus a composite variable, but there are times where it's more appropriate to do a composite versus a latent construct when you're doing that. But multiple indicator measures are much better than single indicator measures. But at the same time, it doesn't do any good if your multiple indicator measure lacks reliability or validity or sound psychometric characteristics. So the next piece we're going to talk about is directionality. Part of specification is determining the direction of effects. So how are you lining these variables up, and what is causing, or you hypothesizing to predict something else? So the direction of effects is what we call effect priority. You, the researcher, you need to determine the ordering of these variables and what is hypothesized to cause another variable in here. One note on this, though, is that when we talk about effect priority and the directionality, this doesn't apply to the indicators for latent variables, because those arrows will always go from the latent variable out to the indicators, or when we're talking about the residuals, the error terms in there. We're talking about the main variables, so the latent and the manifest variables going one from another, that they need to go from a left to a right direction, and they need to have directionality. How we determine what direction and in what order to put our variables largely depends on three things. One, theory, and this is the most common one, is that we have a theoretical reason for why the egg comes before the chicken in this model. We may also have directionality based on time sequencing. So this variable was measured in year 3, and this variable was measured in year 5. And then we also rely on past research that indicates either directionality or time sequencing or causality. Reviewers will often ask you to justify your directionality choices. So it's very important that in your literature review, you set up really clearly the relationships that you are proposing in your model. So as your reviewers read your literature review, it becomes very clear why your model is set up the way it is, and the ordering of the variables are in the manner that you're putting them in. So a quick reminder about causality, because we were talking about cause and effect and directionality, is that we're still doing correlational research. So whenever we're writing about these, we're still going to use the correlational language of association and linked and related, and we're not going to use the causal languaging of effect and caused and impacted. Because of that, and the reason because of that is you really need 5 pieces in order to really state clearly that you have a cause relationship. I'm not going to go into too much detail into these because this is really more for a discussion in qualitative or quantitative research methods. But the 5 pieces that you need are temporal precedence to really show this comes before that and not the other way around. And you usually need to test both in order to clearly show that the direction you're saying is that, and it's not a chicken and egg where they both cause each other. The second is an association, so you have to show that they're strongly associated with you. The third is isolation, to really show that there aren't other variables that are mixing that, but this is really it. The fourth piece is correct effect priority, that it actually is in this order. And then the 5th piece is the known distributional form. So understanding whether this is probabilistic or deterministic causality. SEM usually is assessing probabilistic rather than deterministic causality. You can read more about these in the textbook in Chapter 6 in the Klein book. The next piece is all about the recursive piece of your model. So this is about having feedback loops, having arrows that go forward and backwards or up and down, about how you draw out this model and the ramifications if you draw out your model where there are some feedback loops. So when we talk about this, we talk about two kinds of models, recursive and non-recursive models. I don't know why they call, well, to me these always feel backwards because recursive means circular to me, but that's not how it's used in this context. So recursive models have two features. They are unidirectional. So when you look at those arrows, those straight lines where you just have a single arrowhead on one side, they all go left to right. Again, you're not including error terms, the residuals, and you're not including the factors for latent constructs. The second piece is that the disturbances, so the error terms, are uncorrelated. They are not correlated with each other. So these kinds of models are easily analyzed, easily identified, and easily estimated. They're pretty straightforward when you're doing your analyses. And these are the ones you want to stick with. You want to stick with recursive models. The second kind of models is non-recursive. In non-recursive, you'll have causal feedback loops. So if you look at the diagram I put here on the slide, the green highlighted arrows show you a causal feedback loop, where you essentially have a circle going on in your model. If you look at your arrows, and if there is a circle, you got a causal feedback loop. And one of the reasons causal feedback loops create such issues when you are doing structural equation modeling is you are essentially giving more than one estimate for each model parameter. So because of that, we have all sorts of problems. And it is possible to do non-recursive models, but they're very difficult to get to run correctly, and there are sometimes some real big issues with biases and estimates. The second piece of non-recursive models are correlated disturbances. So that's the orange highlighted one there where you can see the error terms are correlated with each other. So typically specifying a model with both of these creates a lot of fatal errors when you run it. However, as we're going to look at on this next slide, you can run models, and in fact, it's not uncommon. It's actually pretty common, and I've done a lot of these myself where you do have correlated disturbances. So when you look at the non-recursive models, there are two kinds of partially non-recursive models. So if you remember, we talked about two kinds of issues. One is having feedback loops, and the other is having correlated error terms. The partially non-recursive models are all about those error terms. So there are two kinds here. We have bow-free and a bow pattern. So on the left here, you can see the bow-free pattern. This is where we have a correlated disturbance, but there are no direct effects between those manifest variables. So if you look at y1 and y2 here, our two dependent variables in this model, they do not have a direct relationship between them, but their error terms are correlated. So in other words, you have the bow but not the string. If you have the bow but not the string, it's good. And you can actually run these models just fine. And they're treated just the same as a recursive model. Now the bow pattern, however, is where you run into real issues. So that is where you have both bow and the string. So if you look on the right side of this model, you can see on the highlighted piece, you have the correlation between the error terms plus a directionality between the dependent variables y1 and y2. So you can see how this creates kind of this bow feature where you have the directionality plus the correlation there. And when you have that full bow, so the directionality and the correlation between the error terms is treated as a fully non-recursive model, and then you get into all the issues that I talked about in the last slide. So in summary, you need to specify directionality in your hypotheses and when you draw out your model. And this is usually based off of theory and past research or time sequencing. There are two types of models, recursive and non-recursive. And overall, recursive models are good. They're unidirectional. They are unidirectional. You can, in general, non-recursive models are very bad, except for the bow-free. The bow-free works, and they're treated just as recursive models are because they're unidirectional. They have some correlated error terms, but they don't have that string between the manifest variables. Anytime you have a feedback loop, if you can draw a circle anywhere around in your diagram, you're going to run into huge issues with trying to figure out identification. or identifying your model and huge issues with estimation. The next piece of model specification is model complexity. So our goal in drawing a model is always to have a thorough yet parsimonious model. So we want it to be simple yet meaningful, simple yet thorough. We run into issues with models when it is either too complex or too simple. So if it's too complex, it's difficult to develop any kind of understanding or any kind of meaningfulness or any kind of application from the model. It's just, it's too complex, there's too much happening, we can't really do anything with it. If it's too simple, then typically we don't have enough sophistication, we're leaving out meaningful variables, it doesn't have enough in there for us to do anything with. And if that's the case, we usually run into trouble with publishing in good journals, and we also run into issues of really model specification where we have left out critical variables and associations. With model complexity, one of the things that's important to determine, and this is something we're going to cover a lot in the next module when we talk about identification, is evaluating the number of parameters being estimated. The way you do this is pretty simple. You take V, which is your total number of observed or manifest variables. So everything that is being estimated, anything that is being estimated in your model is the V there. So if we had, 6 variables, then we would say 6. In order to figure out our total number of parameters being estimated or the total number of observations we have, we would do 6 times 6 plus 1, so 6 times 7, and then divide that by 2. Now that is for when you are not including mean structures. M plus includes mean structures when it is doing analyses. So when you do that, you just take that same formula, but then add in the total number of mean structures that you're doing. So you just add in V one more time. We're going to cover this again a lot more in the next module in identification with examples, multiple examples of doing this. So don't worry too much now about understanding how to do this. We're going to do this more next week. Okay, the last piece that we're going to cover in model specification is parameter status. So again, parameter is an arrow. Parameter is an arrow that we have, that single-headed arrow or the double-headed arrow. Typically in these, we're talking about the single-headed arrows in our model. And we can have parameters estimated in 3 different ways. We can have a freely estimated parameter. That's the default. If you don't do anything, that's what it's doing. And what it is doing is estimating it from the data. So it's taking everybody's scores, and that's how it's estimating it. So when it's creating that beta value, because remember those are typically regression coefficients, it is finding that regression coefficient from the data in your data set. We can also do fixed parameters, and that's where we fix it to a constant value. So there are some times when we do this, especially in CFA and some of our longitudinal models, when we will fix it to a constant value. We also tend to do this sometimes in multiple sample analyses. So the reason we do this is to kind of test hypothesized relationships between some of those areas. So what we do is we run it first freely estimated, and then we constrain it to be fixed, and we run it again, and then we look at the chi-square and the model fit, and we just subtract the chi-square, the degrees of freedom, and look at the p-value of that. So that is chi-square difference testing. Again, we're going to get into chi-square difference testing in a few weeks. So I just want to introduce this idea to you and what we're going to be doing. Chi-square difference testing is not difficult to do, but it is critical in structural equation modeling analyses when we're doing some of these testing alternative models and when we're doing some of these like fixed and constrained parameters. So fixed is fixing it to a constant value. Constrained is when we take 2 parameters and make them to be equal. This is often done in dyadic, cross-lag, and multiple sample analyses. So what we're going to do here is test to see is the relationship between these 2 variables the same for men and women in like dyadic analysis, or is it the same between these 2 groups of people? So those that are depressed and those that are not depressed, are the relationship between these 2 the same? So the way that we do that is we first freely estimate it, let it be what it is as the data says, and then we say make these 2 things to be the same. And again, we do a chi-square difference test. And if that test is significant, that means our model got significantly worse. And in fact, they are not equal. And if it's not significant, that means that they are equal. So actually, and that's really important information sometimes to get for our hypotheses, to say that, in fact, the relationship between these two groups of people or these two partners are the same. There is no difference here. So again, when we're specifying our models, we may freely estimate, fix parameters, or constrain pairs of parameters to be equal. All right, so to finish out this lecture today, I want to introduce you to the different types of models. I know I've introduced some of these to you before, and I want you to I'm going to show you examples of these, and we're going to have a consistent example as we go across to show you the kinds of hypotheses and questions that come up with these. The first is a path model or a full structural model. So this is just a straight up model. You may have a confirmatory factor analysis in here. You may have mediators and moderators in here as well, but this is just a full structural model. Typically in these models, we're using the kinds of hypotheses and research questions that you've been introduced to so far in quantitative research methods, in advanced statistics, and in multivariate statistics. So we're asking about things like, what is the association between parental warmth and adolescent alcohol use and adolescent depression? What's the association between parent-child conflict and adolescent alcohol use and adolescent depression? That's a common research question that we would ask for this kind of a model. So again, mostly what you've been doing a lot thus far, a lot of the questions are about what are the association of this variable to that variable. We may have mediation and moderation testing, so we may ask, how does this variable, like how does parent-child conflict moderate the relationship between parental warmth and adolescent alcohol use? We may be doing testing of confirmatory factor analyses. And a lot of structural models are also used to develop scales or other instruments that we may want to use. The next kind of model I want to talk to you about is APIM, so actor-partner interdependence modeling. This is dyadic analysis. So in this, what we do is we take the model. So this is the same model we had on the last slide, but we're going to replicate this model again for parents and adolescents. So a matched pair, or for anchors and partners, for spouses. We're going to test this model for both of them, and we're going to have actor paths and partner paths. So as you can see in this example, on the top end, we have the parents' reports of parental warmth, parents reporting on their parent-child conflict, how much they think their adolescents are using alcohol, and how depressed they think their adolescents are, versus the adolescents' reports for these same variables. So this is the adolescents. Again, these are going to be the exact same variables. So the adolescents reporting on their parental warmth, parent-child conflict, their alcohol use, their depression. And then what we do is we check the actor paths. The actor paths are the ones that are in blue here. So they go from me to myself, or from parent to parent, or from adolescent to adolescent. And the partner paths are the ones in green here. So those are like the adolescent's report of parental warmth. How does that impact how their parents view their depression, or how their parents view their alcohol use? The actor paths tend to be, that is where what we are most interested in when we are doing dyadic analyses. So typically in this kind of analysis, we're going to have a lot of the same kinds of questions we've had before, but we're asking them we're going to have essentially two kinds of research questions or hypotheses, the anchor and the partner. So the example I gave you here is from one of my articles. So the anchor is, in what ways are men's and women's acceptability for online boundary crossing associated with their own reports of online partner intrusion, yada, yada, yada. Where the partner path would be, in what way are men's and women's reports of acceptability for online boundary crossing associated with their partners? So it's women's to men's and men's to women's. If you're doing opposite sex only research, if you're doing same sex, you would structure it as an anchor and partner, so that you're looking at men's and women's reports to their partner. So we can still do mediation, moderation. We can have it be longitudinal, multiple group. We can still kind of do those same kind of things. I have an article I'm working on right now where I've done, where I'm currently analyzing, looking at a dyadic analysis, but also doing multi-group analysis where I'm looking at the same thing for same-sex and opposite-sex couples. And in the opposite sex, I'm actually doing opposite-sex couples, same-sex gay couples, and same-sex lesbian couples, and looking about how this model looks different across those groups. So keep in mind too, when I'm talking about these different kinds of models, they're not isolated. You can combine them together, so you can do a dyadic and a longitudinal analysis. So the next kind of analysis I've already talked about a little bit in the last slide. That's multiple sample analysis or multiple group analysis. So in this one, what we're doing is we're taking this model, so we're going to take this same model we had back on that full structural one, so parental warmth and child conflict impacting adolescent alcohol use and adolescent depression, and we're going to test it for different groups. So this is where we really combine ANOVA with SEM. So for example, for this one, you may compare intact to blended to single parent families with this same model. So what we're doing in multiple sample SEM is we're asking, again, the same kind of questions we talked about before, but we're adding into it, are there differences between these groups? And what are those differences in there? So basically, we're applying ANOVA to structural equation modeling, or bringing in ANOVA plus multiple regression into a single analysis. So generally, when we're doing these multiple sample analyses, we're looking to explore possible moderation, because we're looking at interaction effects when we're doing multiple group analyses to see if there's an intervention that makes a difference. The difference between the groups is the intervention, or to see if there's any difference between groups, classes, types of people, like I talked about in the past examples with opposite sex and same-sex couples, or intact versus blended versus single-parent families. You can do a lot of these differences or testing out differences between samples. I've also looked at this in my research, looking at computer-mediated communication, looking at differences between cultures, so looking at like Brazil versus Japan versus Europe, because the way that media is used in those three regions of the world are quite different, and you can learn some things by looking at those differences. The next kind is a longitudinal analysis. This is autoregressive models or cross-lag autoregressive models. So in this, what we are doing is we are looking at the same variable across time. So like an example here, if you looked at just the blue, so let's take away the green, that is a straight up autoregressive model. So what we're doing is looking at the stability of this across time. Now when we add in the bottom part, the green variable, so when we have both adolescent alcohol use and parent-child conflict across time, this is a cross-lag autoregressive model. It's cross-lag because you've got the cross piece. So if you look at the blue arrows, that's the cross piece. So what we're doing here is we're looking at the stability of adolescent alcohol use as well as parent-child conflict across time. That's the green arrows. And typically what we would do is we would constrain the green arrow for adolescent alcohol use in each of those time sequencing. And if our model gets significantly worse, that means that they are significantly different. So in other words, adolescent alcohol use is unstable across time. Versus if we constrain those to be equal, and our model does not get significantly worse, and that means that it is stable across time. When we're doing a cross-lag model, we're also looking at how does parent-child conflict influence alcohol use, and vice versa, alcohol use influence parent-child conflict across time. Autoregressive models are really important because they help us to better determine cause and effect, because we're looking at the same variables across time. So we're seeing both sequences of how they impact each other. The other piece that we know also that's really important for variables is that the biggest indicator of my future behavior is my past behavior. So we can also, what you can see in this model is like for age 15, we can look at the impact of parent-child conflict on adolescent alcohols 2 years later, age 17, while controlling for the adolescent's own alcohol use in the past. So autoregressive models can be very important and critical in evaluating time sequencing, cause and effect, stability, and also accounting for one's own past behavior. So the questions that this asks are mainly about stability of factors across time. They also ask a lot about relationships to change of these factors across time. When we get into the cross-lag models, which was the example before, we also get to ask questions about the concurrent association between two variables at time 2 and the stability of those across time and how they impact each other across time. So like, do earlier levels of X, so do earlier levels of parent-child conflict predict later levels of adolescent alcohol use. So autoregressive models are a very important kind of longitudinal analysis and are really fantastic to use, especially in secondary data analysis, where people have been asked the same questions across time. You can very easily develop an autoregressive model. So the last kind of model we're going to talk about is, again, a longitudinal model. This is latent growth curve modeling. So latent growth curve modeling is all about understanding where people start and how they change across time. So essentially what you're doing is creating a CFA, and you're having the intercept, which is the starting point, and the slope, which is the linear change across time of a variable. So you can see here we have like adolescent alcohol use at age 13, 14, 15, 16, 17. And then what we're doing in here is we're looking at the starting place and the slope of that across time. Now what we eventually always do in latent growth curve modeling is we add in a covariate. So for example, we would add in that covariate of parental conflict to see how parental conflict changes the intercept, so the starting amount of alcohol use, or even potentially the starting age of alcohol use, and the slope, so the linear change of alcohol use, how much it increases or decreases across time based on the covariate of parent-child conflict. So when we're talking about latent growth curve modeling, we're really asking about how does this change across time? You know, so like how does relationship happiness change across the transition to parenthood? How does adolescent alcohol use change across adolescence while accounting for parent-child conflict? You can, and that piece is also that second piece there, so you can relate variations in growth trajectories to covariates. So how does parental education affect trajectories of relationship happiness across the transition to parenthood? So this is probably the better example here is, you know, how does adolescent alcohol use, or sorry, how does parent conflict affect the trajectories of adolescent alcohol use across adolescence? When we're doing growth curve modeling, the last piece here is that we really have two levels of analysis that we're doing. We're looking at differences within individuals and then also differences between individuals. And there are ways, we're probably not going to get into them this semester, but there is latent growth or growth mixture modeling when we're looking at different classes and groups. And there is also curvilinear growth mixture modeling or curvilinear latent modeling where we can look at curvilinear changes across time rather than just linear changes across time. So in summary, specification is the first step in the process of developing a structural equation modeling. Specification is the representation of your hypotheses in the form of a structural equation modeling, and that the first and most common error in specification is leaving out critical variables. So specification is that very first part, you know, where you can start drawing out your model and you start to develop your hypotheses by indicating which arrows go and where and in what sequencing the variables go in. And you want to make sure you have in the important players, not only the variables you're most interested in, but the others that other researchers have identified are critical key variables in this research domain. It is best, but not always, to use multiple indicator measures. So we want to have manifest or latent variables as much as possible in our structural equation model. Our goal is to have a parsimonious but meaningful and impactful model. Something that people will care about and want to know about and has enough sophistication to have some of the other variables and to have enough in it to really be meaningful and impact change. When we develop those parameters, the arrows in there, they can be estimated either freely, so how the data indicates, we can constrain them to be a certain value, or we can take pairs or even more than pairs, we can do two or more parameters and constrain them to be equal. There are many types of models that we can do, and understanding the possibilities of different kind of models helps to open up your mind to different potential kinds of questions and hypotheses to ask about. So because your mind is the most important tool in order to do research in structural equation modeling, it's important to know what kind of possibilities there are out there what kind of possibilities there are to investigate when you're doing your analyses. Next, we will cover model identification. So once we've covered the next module on model identification, you have everything that you have in order to start to run your model. And then in 2 weeks, we'll cover model estimation, so how to actually do that piece.